Thank you. Hi, everyone. I'm Everton Fraga. I work for AWS as Senior Blockchain Specialist, SA, that's Solution Architect. And that means that we help companies, businesses, individuals, startups, and businesses of any kind. They want to migrate to the cloud and succeed in their workloads. So, just a little bit about me. I used to work for the Ethereum Foundation previously for over 4 years. I worked on the Mist project, so there was the dApp browser, also a little bit on the Ethereum wallet, and some other applications like the Grid was a tool for providing a graphical user interface for Ethereum nodes. And then lately, I worked on the Ethereum JS set of libraries. And well, it is a big pleasure to be here. I wish I could go to France, but due to well all the travel bans concerns, I couldn't. So I'm based here in New York City, but I'm originally from Brazil. So let's get started. Here for our session today, we'll talk about creating fast, scalable RPC APIs using the power of Amazon Web Services and 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 let's review the agenda here. So first, we'll talk a little about latency, and then concurrency and elasticity, processing time, caching strategies, and then we can talk a little bit over how to optimize even further. All right, so let's get started just with some level set. Um, on Ethereum nodes, you have well two networking stacks. We can, so to say, you have on the bottom part the peer-to-peer networking that works on ports 3033. That's basically for UDP and TCP. So it allows node discovery and synchronization. There's also one other port, but that's for boot nodes. That's 3031. And there's on the application layer, what users and applications would actually use are those on the top half. So you can see 8545, that is the JSON RPC endpoint. You also have the WebSocket interface, you have GraphQL as well. And so we'll talk about this top half, so application. So just a note about connectivity here and how does that represent your reality. So let's talk about these RPC and latency from this RPC angle. So it is basically mostly influenced by the physical network route that all those packages need to go through, traversing the public internet until they meet your actual node. So here on this map to the right, we can see represented in white, it would be your Ethereum node, like hosted in the US, for example, and then a user in South America trying to access it. It would go over the public internet at first, right? And it is also, of course, influenced by the physical location of these servers. So let's move on. Here in this example, we're picturing, yes? Oh, okay. Let me try again. Wow, thank you. had some permission errors here from Firefox. Let me try again. Okay, cool. Yeah. Okay, we just got to the graphical part, so no harm. Thank you for letting me know. Okay, so now going to this map representation. Here we have a node in the US, and we have like users all over the globe. In this particular case, what will happen, regardless of the infrastructure provider you use, um, by default, all those requests being made, they would traverse the network over the public internet, making several hops concurrent to many other information that's traversing there. This can provide some more added latency, given that it would be really competing with many other people or applications. So AWS provides several edge locations. Not only about regions, but we're present on several parts of the globe. So instead of having those requests being traveling the entire or half of the world just to get to the node, we could have those users accessing specific AWS endpoints, and then those requests would then turn this in these orange lines. Those are really faster connections backed by AWS backbone. So they got transocean cabling just specifically for AWS customers. So that really helps in these cases. But then, okay, we kind of help to solve the how you're competing with those requests. But then there is also, I talked about the number two, which was the location of those servers. So you can even optimize that further, deploying your application to your Ethereum nodes to several regions. So here you would have a really simplified version of it, because there are many more regions, but we're gonna see in a few minutes. But each user would access their own the closest region and nodes that are deployed there. So just giving here an idea of how can we achieve that. So introducing those, two services. Cloudfront is here, and both services are here for quite a while. And so Cloudfront, it is a CDN, but not only that. So they are present on those edge locations, and they take multiple origin types. So it is mostly used for content delivery networks. So it is a lot with S3, that's the storage solution. But it also can take several other origin types. So in this case, servers or load balancers, or even playing HTTP URLs. The good news is that it supports both the RPC methods, like in the HTTP or WebSocket. So you could achieve first these using CloudFront, and even these as well. And Route 53, it is AWS DNS service. So you can have it all working from a single URL, from a single domain. So it would detect, it allows you to configure specifically what would be the routes for every region. So a user in Asia, to make sure that a user in Asia can access the content really fast from APAC region. So Japan, Singapore, or any closer region. And of course, both services offer some security capabilities. So DDoS protection and several other rule-based access control and several other security features. And this is just a little bit about the global infrastructure. So the charts before were really simplified, but here we can have a better idea of what are the edge locations, the points of presence for AWS, and where you could access, you could place your servers there. So the orange circles are the regions where most of these services that offer it. And the blue and purple dots are edge locations. So there are a selected services that are offered there. So you can place those Cloudfront distributions. And then whenever a user accesses that edge location, you would have a high-speed internet rail to access your servers. So that's pretty interesting for the latency part. Just as a curious fact, this is how it looks like in Europe. So it's got pretty dense. All right, we can talk about concurrency now. So it is basically the concept of how many requests you can handle at the same time. So let's now look at just like one region. If you deploy your application to a specific region, if you have just one node, it would have a limited capacity. When the capacity overflows, your node will be more exhausted. It might be with higher CPU usage. Excuse me, or with the load average will be skyrocketed, making every request, any new request, take longer. So we do not want to exhaust our nodes. So what we typically do is to deploy another one, and then you can scale or horizontally to meet the needs and the user demand. This is typically achieved with this mechanism here. So we have first a load balancer that would distribute the load to one or more servers. But then when you want to just add a new server to this region, we can just use this what we call auto scaling group, which is a set of automated rules we can place in order to determine when should we spin up new servers or shut them down when you have lower incoming requests. So it is really solving kind of two problems. One is the cost savings, because you're not over provisioning resources for your use. The second is adding the elasticity, because it meets your API demands. So we can have a brief spotlight here with those two services. So you can, with the load balancer, you can distribute traffic among multiple targets. It supports multiple availability zones for failover. So availability zones are an interesting concept. So inside a region, let's say US East 1, there are multiple availability zones that are pretty much data centers. Those are interconnected by really high-speed fiber connections, and they are used for failover. So should anything happen with one region, the other one would, if you configured it properly, so you could route your traffic just to the other one that's up. So these different data centers, they use even redundant power. They use different different services, different utilities, so they shouldn't be affected. There shouldn't be more than one availability zone affected in the case of anything bad that happens. And these auto-scaling groups, those are based on rules, so you can deploy or shut down those compute instances with the idea to maintain your performance and again only pay for what you need, so you wouldn't end up with a huge bill if you just left those servers running, let's say on the weekend or during the night. There's one thing here though. When you deploy new servers, given that we are in Ethereum world, you have to sync those nodes or at least get some backups and restore them. And by experience, we've seen that this thing can take a while. So for syncing, due to the incredible work by the Geth team and several other people involved, they can achieve with SnapSync something under 5 to 6 hours. You can sync a full node. But then it might be a lot for depending on your business needs. And if you want to just restore a backup that you're making yourself, it can also take quite some time and then more operational burden. So you would have to manage those backups, automate them, and then sometimes you would need to stop one server, take the backup, save it, store it elsewhere, and then turn that server on again, turn that Geth on again. So there are several considerations on why you would operate your own Ethereum server this way. So here we have this service called Amazon Managed Blockchain. It was launched in a few years ago, but first it was only for Hyperledger Fabric. That's a private blockchain. And this year we had the general availability for Ethereum instances. So it is a really, really easy way to deploy full nodes using Amazon Web Services technology. So from the console, you can just click on launch instance, select your network, select your instance type, choose the availability zone, and that's it. When you click on create, it would take like under 30 minutes for testnet, under 1 hour for mainnet. Then you have a fully synced Ethereum node at your disposal. So it is fully managed, and that means you as a customer don't need to worry about managing the storage of that instance or managing the uptime of it. So the service takes care of these things for you. The same thing with patching, software patching, updates to Geth nodes. So we have an upcoming hard fork, and the AWS team is responsible for that, and will make sure that every node will be updated on time. So it is available in several regions. So it has support for one of those architectures I showed you in the map. And there are also several instance types available. So you can have or general purpose using the T3 family, compute optimized using the C5 family, also the memory optimized using the M5 family. And they are, they're easy to integrate with other AWS services. So they're like a first-class citizen within the AWS family of offerings. So they provide proper endpoints for you. So when you spin a node, you would have access to an HTTP and a WebSockets endpoints. So you can use them behind a load balancer or expose it to your application. So really, you choose how to operate. Moving on, let's talk about processing time of those requests. Well, it determines how many requests per second a node can serve. If well, that's an obvious statement, but I guess that's a good start. So you can have several use cases, right? So you can have CPU bound RPC methods or use cases. Some other use cases might be more memory bound or network bound. So it is really, really important to identify your application needs, do several benchmarks, so you can really understand what is the specific instance that you need. It can make a big difference, and especially in the billing, right? So if you're using an instance that's not ideal for your use case, you might need more of that same instance, and then that might cost you. So as I mentioned before, um, on Amazon Managed Blockchain, you have the compute, memory, and optimized. But this is actually a general concept. So you will find on EC2 page, that's the Elastic Compute Cloud service. You have a whole list of instance types, so you can see if you have a really large need for networking, you can check there. There are many instance types and sizes available for networking intensive workloads. Same thing with memory or I/O. So that's actually also important. Uh, so when you're syncing your Ethereum node, well, it would require lots of I/O. So you can have so by having a I/O optimized instance, you can really take advantage of it, and it makes a real difference for you to use that. So let's get to this tricky thing called caching. By now we have already just yeah, okay, yeah, this, okay. Yeah, but at this point we have already talked about latency. We talked about concurrency and elasticity. So let's take our API as an example. So it is already distributed in several regions. It already provides low latency access to my users. It auto scales based on demand. But what else should we aggregate to this architecture? So it would be interesting if we could make all that using a cost efficient way. Um, so caching really helps with this job, and also helping with the request processing times. So you can have like depending on the service mix you use, you can reduce those requests by an order of magnitude. So caching is kind of tricky on Ethereum land. So let's talk about that in a minute. And by some observations, I could see that most requests will be from ETH calls that requires EVM processing. And then by the end of the presentation, I'm going to talk about almost by the end of I'm going to talk about ways you can optimize that. So first question is, what can I cache on Ethereum, right? So the easiest part is the static queries. So you can have like protocol version syncing, net listening if that's relevant information you want to expose to your users, as long as peer count or net version and well chain ID. Chain ID will be the same for the same URL endpoint you're using, so you can safely assume that it would never change. So you can pretty much have a static cache for that, something that will kind of never expire. So we'll have a really um, far in the future expiration date. Then you have some other, let's say, immutable, quote unquote here, um, results. So you can have blocks by number, block transactions, um, the count of transactions by block hash, and then, well, transaction by hash, and then the list goes on. I put the quote unquote here for a very particular reason. Um, we've been experiencing a lot of discussion regarding miner extracting value um, and all the reargs. So it seems like there are groups organizing to create to push for reorgs to extract more value from the chain, and so front running on these things. In the event of reorgs, you'd have to be really careful with how you're saving your cache keys here. To have a good way to provide stale cache, so you're always providing accurate information to your users. So these methods here, they take like one parameter most of them, if I'm not mistaken. Some of them would take the block parameter, so that adds lots more complexity. But here, they take more than one parameter, so it starts to get um, dense in the amount of cache that you would save. And then here we have the category of what I cannot cache on Ethereum. So it would be, you could even try to cache those things. Of course, it is possible, but I wouldn't recommend you to cache all ETH calls because those are they are the byproduct of some EVM processing, and they might have different calculations even for the same um, even for the same input that you put on that ETH call, depending on the block number, the ETH call might result in something else. So effectively, you would not guarantee an accurate, a consistent response to your users. Estimate gas, so that's basically simulating a transaction that's also CPU bound. There are ways you can try to simulate these estimate gas, but it requires you knowing in advance what is the destination address, what is the origin, if they have enough balance. So if you have an application that your users access ETH estimate gas a lot, like for the same token, maybe you can even rewrite this method and try to understand, instead of raising all the EVM for every request, you can try to decouple this estimate gas into some other request that would access, let's say, the origin and the destinations count balances. Check if the destination is a contract. Maybe if the destination is a contract of interest, you might already have the typical gas value for that kind of operation. So you would also take the method, the data being accessed. So the method that transaction would access, and then you could have with some heuristic, you could just provide a compatible gas estimation for those users. Well, filters are stateful. Those are stateful, so there are some considerations here. The first is the filter is a node based. So if you have a load balancer with 2 Ethereum nodes here, and you first land on the first one, your request lands on the first one to create a filter. Then you'd have the filter ID. The next time you access that node asking for the filter results, you would have to land on the same node. That would be a good strategy. So there are two considerations on this. The first one is that you can define some rules to have sticky sessions, what we call. So whenever you do the second request, the application here in the middle, we can make a proxy or maybe a load balancer configuration for that. It would identify what was the node that you sent for the creation of that filter. Then they will route you to the same server, to the same Ethereum instance over and over again. That, of course, if you have a pretty dynamic rotation of instances, let's say if you scale up and down several times during the week, and you have applications that consume that data on a large period of time, so you might want to maybe even abstract the filter functionality. So you could save, like, let's say on a separate data structure, what is the who's the client, the user making those requests, and storing also the filter ID and all the information regarding that filter, so the parameters. So should anything happen with that, with one specific node, you could via a proxy, via proxy, we can talk about proxy in some minutes. You could just get that same information from this data store, and then you would have information of those parameters. So the address, maybe let's say we're talking about smart contract events filtering. So you can have the contract address, the topics you're looking for with the parameters, and then the last block you had access. So the next time you try to access from, let's say, an instant, your client trying to access that specific filter ID, you can look it up and see, hey, I think I don't have that instance anymore. So your application can recreate that filter, and then you can start from the block you stopped last time. So you can create a somewhat resilient filter mechanism using this. Same thing with block filter, pending transaction filter. Yeah, so these are, you know, the hardest methods to leverage from cache. And if you want to really go on a reasonable, fairly big scale, you have to treat them kind of one way or another, right? Yeah, so we have those stateful queries, filters, subscriptions. We can also talk about Mempool. Well, Mempool is shared across several nodes. It is not the same. Every node will have their own version of a mempool, and some services even implemented their own mempool. So they create a really big shared pool for several users. Well, it is interesting because you can have consistent of the data, so the same principle as the filters, but what would dictate that for your application is really your specific needs, right? Yeah, so some considerations on caching. You got to be really careful with stale cache. So stale cache is something that you save and then you fail to update that information, and then but users would still request from that specific cache. So then you're basically serving outdated information to users. So that is kind of well, that's non-ideal. There are some strategies. So instead of, let's say, using creating one cache key for latest block, so whenever people request information from from the latest block, you would just serve that key. If you fail to update that, you would only present outdated information. But then your application can do something like request latest block. That's a cheap query, inexpensive query. And then you would update have the cache key as the block hash. That's important. And let's say some identifier like block, and then the block hash, and then you have all the information regarding the very block. So doing 2 requests might seem to your node from your proxy to your node might seem non-ideal, but it might be really faster in some time. So you really got to do some testing and benchmarks here. If you have something like a filter for new blocks, and then you have these as a cache key, that will be interesting. So must handle reorg seamlessly. This is, of course, kind of tricky as well, because if you save, let's say, a cache key for block 1 million, but it got changed, and those by a better block with higher total difficulty, then your users, again, will be seeing outdated information. So it is ideal to use those block hashes as keys as much as you can instead of numbers. And then you can make those requests. So you can even save, let's say, if you have an elastic cache, or if you have an elastic cache, you can just put entire JSONs of representing those blocks there. Then you can query them by hash, and then you can even have another data structure where you would save the hash to number, or the number to hash association. So whenever a user wants to grab, like, what is the blocker number 1 million, and you want to fetch from cache, you would use this as a secondary index, where you would first request the number to hash data structure, and then you request the actual block. So this way you save on storage for your cache structure. It makes easy for you to keep consistency. So whenever there is a reorg there, you would only need to update this index comprising of the number to hash data structure. You wouldn't need to update several block JSONs and for block information, because those be on block hash keys, and that wouldn't make much of a difference. So here in Service Spotlight, we can talk about these 2 services. So you have Amazon Elasticache, uses Memcached or Redis as compatible APIs. So they provide you sub-millisecond response times, which means they are pretty fast. They're fully managed and scalable, so you don't have to, again, worry about managing the software, OS patching, anything like this. And well, several applications that are that have a latency as a critical to their businesses. They've been using Amazon Elasticache quite a lot. So financial services, crypto exchanges as well. So people would extract the useful information and sometimes even pre-warm these cache structures on Amazon Elasticache. And then their users would read directly from it, saving your nodes from exhaustion, and even saving on even providing you cost savings, because it is more inexpensive to make those queries against the service than your own Ethereum node or any other compute node. The other here is AWS Lambda, a pretty interesting service that is a serverless compute unit, which means you can just upload your piece of code it could be Node.js, Python, Go, Java, and then it would you can define the entry point and even the destination of those functions, and then they will run on this serverless fashion. So it will also take care of provisioning the right compute resources for it. It is easily scalable. You could even have provisional concurrency, so you could already have some decent amount of AWS lambdas just waiting for more traffic, more concurrent access. And it's, again, pay only for what you need and for what you use. So it is billed by the millisecond. So it kind of incentives you to write, more performant applications, and you would only pay for what is fair for what's being used. So there are some patterns here that you can do. So you can use the load balancer that I talked before. Let me just come back here on some slides. You could use here like a load balancer, and then you could have your lambda function here in between. Okay, cursor here. You could have an elastic load balancer, and then after it, you could employ a lambda function. This lambda function could act as a backend of your public API. And then you could even decide what are the cache keys, send request them from Elasticache and serve your request in a very performant way. So there are some other optimization strategies that are worth talking about. It totally depends on your use case, but here I think that we covered all the 5 main points of the agenda. We can talk about more on performance here. So when I mentioned here on the ETH call method, one data that's worth sharing is, from my observations, most of them were to get token balances. And on standard token representations, the GetBalance method is just pretty much just reading from storage. But then it requires to load the EVM and to process that, the message bytecode, and run those opcodes until they get to the actual storage and return it. This is more costly. So on some experiments, I had some interesting results here. So we could get, like, using less CPU, we could get even over 20% more throughput using less CPU, which means you could even, if you have that at scale, that can represent significant cost and processing savings. So the idea of ETH call optimization for GetBalance is to first identify which are the contracts you want to optimize, and then you could read you could try to or find on their source code to do some static analysis. There is some tooling for that, to find what are the storage position for the balances mapping. And then that would be the exact, and then you can calculate what will be the GetStorage at method, that is a storage bound RPC method. This 1/3 from the bottom. It does not, this GetStorage at, it does not load the EVM. It just goes straight to the storage of that particular account, based on the address you provide and the storage key as well. So you can effectively override the behavior of ETH call into a that is an intense and CPU bound operation into a storage bound operation. And then you could even cache GetStorage at results for a particular block, let's say, with that. So if you get, let's say, in the most optimal scenario, you would get a ETH call. You would translate it to GetStorage at without having access to any data from the blockchain. Then it would just check if you have GetStorage at in your cache structure. If you have it, that's awesome. If you don't, you would just perform one storage bound query. So this way you can optimize it. There are other techniques and ways you can achieve just by using these AWS Lambda as a backend or any other compute just to override some of these RPC methods. So one other example is you can create your own RPC methods, providing useful information that the default set of RPC methods do not provide by default. So you can have a method called, let's say, Everton underscore get token metadata. So I've seen people doing similar things. And then you can have, well, just the address as a parameter. And then internally you would make the appropriate, the proper calls to the Ethereum, to the chain. And then you can have, well, the token metadata, just like it could be symbol, decimals, and the information you want. There are other interesting RPC methods that worth sharing, especially if you work with tokens. That is the debug family of methods. So you can pretty much have an insight on exporting all the storage slots for a particular contract address. And then you can maybe cache all these balances, or maybe just export it for analytics purposes. It would require the same kind of calculation for the GetStorage at. As I mentioned, these storage slots, they're for, let's say, a mapping, down the low-level data structures, they're not saved with just the address of that account you want to look up. It is actually a hashing function over the address you're looking for and the storage slot position. And each token implementation can have this different one. So it requires some knowledge of some specific contract implementations, but it's actually not hard, and the benefits can be really, really good. So you could effectively have all balances of a given token on your Elasticache, providing like sub-millisecond access to it. That might be useful for analytics and accounting. Might be useful for for RPC access for end users, or you can even, instead of Elasticache, pull them for other data structures and other data pipelines. There is one undocumented method on Geth. That is two methods, in fact. That is the debug get modified accounts by hash or by number. This is actually an awesome method. I came across it just recently. And what it does is provide exactly what are the accounts that got changed in their account hash. So storage, balance, nonce, and code. So every of these four fields could incur in an account being modified. Then you can really more easily do cache eviction if you're saving, let's say, things by information by account. You can really easily know when that account was changed and then just perform there. So for some cases that that's just a, let's say for token contracts, you have the event, and you can easily know whenever you have an event regarding specific transfer. But there are other cases that you don't have it, so such as maybe Uniswap asset prices on a token pair, or maybe a transaction of Ether that landed on a specific account. So this way you can easily monitor and have just a small list of accounts that got changed for every block. That's really powerful, or a block range, right? Uh, and then you can query this by block number or by block hash. So those are two ways of doing that. One consideration is that to use these two methods, you would need to have all those pre-images, which are basically the recipe to create a given hash. So I mentioned before on how you can generate those keys based on account and the storage position of a contract. Then having these pre-images being saved, you can even know and do the reverse, kind of the reverse hash to know what it had before, and just recreate that more easily. So this is a prerequisite for these debug methods. So if you're running your Ethereum nodes, well, if you're running an archive nodes, you probably have it already. But if you're running full or snap sync or fast nodes, you would have to use a flag to enable pre-images recording. You can also export the pre-images database from another node. So that would just kind of instantly give these capabilities to regular nodes theoretically. And let me see. So there are several ways you can work with scaling your APIs, and just doing a review here. So you can, first of all, just start with one node and use it for, start with one Ethereum node and then make use of those networking services from AWS to have them on high-speed internet rails, so you would have requests being fulfilled more quickly. Or you can have a multi-region deployment. Also, you can deploy more instances, being them Elastic Compute Cloud, like the EC2, or Amazon Managed Blockchain for that, and you wouldn't even need to manage those servers. And then you can add more nodes or shut them down depending on your use. So this way you can handle concurrency better. Then you can handle the requests per second for each node by caching or optimizing those RPC calls. So yes, I think it will be it for today. Again, it is a pleasure, although I'm not there with you, but I would really love to. But it is a pleasure to have the opportunity to relay some information regarding it. So thank you so much. Okay, thank you. Yeah, thank you so much. Bye.